Hello, a great welcome to this series on Abaqus. Myself Jarajan P. This is tutorial number 3. It explains the modeling and analysis of a beam covered in plan. Please note that the link for the playlist for all Abaqus tutorials is given under the description of this video. So let us first read the problem statement. So the beam that we will analyze today is covered in plan, and as you can see that it has a semicircular profile, and the material for the beam is steel with an E value of 2 into 10 raised to 8 kN per meter square and a Poisson's ratio of 0.3. The beam is subjected to a vertical load of 10 kN per meter. As you can see, the beam has 3 supports, one each at its ends, and the other support, that's the interior support, along the vertical axis of symmetry. The beam has a rectangular cross section of 100 mm wide and 300 mm deep. So what makes this problem unique is it's a beam curved in plan. So you know that in this case, the resultant load as well as the reactions, they do not lie along the longitudinal axis of the beam, and accordingly every cross section of the beam will be subjected to torsional moments in addition to the shear force as well as bending moments. Further, in this case, you can see that the beam can be easily described in a 2D plane, whereas the load acts in the vertical to this plane. It means as far as Abaqus is concerned, it will be a three-dimensional problem. In order to help you understand better how does this beam look in reality, here I have attached in the right corner the floor beam, that's a curved floor beam that is supporting a balcony. As you can see that it has 3 supports, one at each at its end and an interior support as well. So let me take you to the Abaqus. Okay, so first we shall proceed for setting the work directory. From file, go to the set work directory. Here I have set it as a C Abaqus tutorial. So remember this is the folder where all the Abaqus files will be written. So that's okay for me. So let me save this model right in the beginning. Save as. So I will call it as curved beam. So curved beam dot CAE. So this is my model database. Okay. So now let us start with the part as usual. So go to the part, and in the part we'll create a part corresponding to the beam. So I'll call it as beam for the easy identification. My modeling space will be 3D, deformable type, and the base feature will be wire. Continue. Now let us proceed for creating the semicircle profile for our beam. So what we can do is we can go to this item, that is create arc using center and two endpoints. So it will prompt for the center point. Pick this point, and now a start point, that is to say minus a 30, and then an endpoint, that is a 30, because we know that the radius is 3. So you can say that yes, we have created our semicircular profile. So you can press the done button. Okay, fine. So now we shall go for the property module. The property module, we have to create the property, create a section, assign this section to my beam, and then finally go for assigning the beam orientation. These are the 4 items to be performed under this module. So let us proceed for defining the property. So the material for easy identification, I'll call it as a steel. Okay, select the mechanical, and we are interested only in the elastic properties. So proceed for defining the E value 2E8 kilonewton per meter square, and the Poisson's ratio will be 0.30. Remember that in this tutorial we will use kilonewton and meters. So okay for me. Now we shall proceed for creating the section. So let us create the section first. Okay, so let me say that it's a section beam. Okay, so the category will be beam and the type is also beam. Continue. Okay, now here you can see that it asks for the profile name. We have not created any cross section, so we are going to create a profile for this beam. It is essentially a rectangular cross section. So click the create beam profile. It's a rectangular, and the profile will identify, because as such there is only one beam here, profile beam. Continue. Now we shall define say point 30.10. Obviously the orientation need to be checked later, so you can say that okay. So that's okay for me. So I created a section. Okay, I created a section for my beam. Now what I need to do is I need to assign this section to the beam. So it asks select the regions to be assigned. So this is my beam. Okay, done. So my section is a section beam. Press OK. Now straight away what I will do is that I will go for assigning the beam orientation. So just click this. So it will ask you select the regions to be assigned a beam orientation. Okay, so obviously this is a section to be assigned to the beam orientation. Done. Now here you will find that it has set automatically the tangential directions. So this is an approximate n1 direction, that's the tangent vectors is acceptable to me. And now you will find that the two directions, that's the normal to this. So that's the n direction is also set. So that is okay. So now once this is set, you will find that the color changes, indicating that the cross section is rightly assigned to it. Now obviously, as I told you, at this stage it is important that you check the orientation of the beam cross section. So for that, go to the view and go to the part display options, and then just highlight render beam profiles, apply. Okay, so it looks to be all right for us. So what you can do is that you can set, so yes, you can say that the depth is oriented in the right direction. Yes, so this is the, let me just zoom it a little bit. Okay, this is good enough. So as you can see that we have set the beam orientation in the right way. This is our depth and this is the width. Okay, and if you have not assigned it properly, you have to go back to the profile section and just edit this cross section. Okay, right now it is acceptable to us. So the property definition is complete at this stage. Now I want to tell you that you can also create a profile section here as well. Create a profile and then go back to the create section. These are the two ways available to us. So now let me, for the convenience, let me go back and then disable it. Part display options, just disable it here. Okay for me, and I will press the XY. So we have completed the property module. Go back to the assembly. Remember we have only one part. Create an instance of this part. Okay, so dependent mesh part. Okay, okay for me. So the assembly is over. Now we can go straight to the step. Okay, in the step we can create a new step. That is our main analysis step. I will call it as a step beam, and obviously we'll place it after the default step created by Abaqus, that's initial, and analysis procedure that we select will be the static general. Just continue it, and we will keep all this parameter as default as same. Remember that nonlinear geometry option is set here as off, because this is not a large displacement load. Okay, other options will keep the same. Okay, so it means that we have created the step as well. We can proceed directly for there are no interactions, so accordingly we can proceed directly for the loads. So the load module essentially consists of specifying the boundary condition as well as the application of the loads. So now we know that we have three supports, one at this end, one at the right end, and the other support on the vertical axis of symmetry. Now the problem is I don't have a point here on which I can apply the boundary condition. So in order to have this, what I will do is that I will split this beam into two using the partition option available in the part. So what you can do is that you can go straight to the part, okay, part, and in the part what you can do is that you can go for partitioning it using the partition edge option, select midpoint. So what you can do is that select a point on the edge where you want to do the partition, is the point, and the create partition. Now here you will find that after doing the partition, okay, this single beam, it is split into two beams, okay, two beams, okay, and you also have a point here where you can also apply a boundary condition. So now what we can do is that we can go back to the load module. Okay, let us just start prescribing the boundary condition first. Okay, so what we can do is that we can have a boundary condition known as pinned boundary condition BC pinned. Okay, BC pinned. Select the mechanical category, displacement rotation, continue. Now it will ask for select regions for the boundary condition. Obviously, we have only 3 points that we need to select. So we have selected one. Press the shift key, select the other point also. We have selected this point, and also we have selected this point. So we have selected all the 3 points where the boundary conditions are to be applied. So done. Okay. Obviously, we know that here we have to restrain the U1, U2, and U3. Okay. So that is okay for me. So as you can see that yes, we have generated the pinned boundary condition at the 3 locations. Now we can straight away go for the definition of the loads. Okay, so we'll say that this is my beam, load beam is the loading I have named it. And obviously this has to be created in the main analysis step, which we have named as step beam. And this is a mechanical category, and the load is a line load we know. So continue. Now we have to create the bodies where the loads are to be applied. Okay, so please select the 2 parts using the shift key. Okay, that's it done. So now you can say that the loads, it's a uniform load we know, and in the one direction it is 0, the second direction is also 0, and the third direction we know that its value is minus 10. It is downward. So okay, so you can say that it is in the plan. So if you want to see the loading direction, you can say that yes, we have rightly. Yes, so this is your beam, and you know that the loads are acting in the downward direction. Okay, fine. So this means we have applied the loads also correctly. Now we can straight away proceed for the definition of the mesh. Okay, fine. So as far as the meshing is concerned, here we have to see only 3 things. One, creating a global seed. Okay, it says that dependent part instance cannot be edited. So for this, instead of the assembly, go to the part here. Okay, set the global. So let me see that I want to split this into segments of 0.1 meter. So I'll specify the size is 0.1. Let me see whether this is okay for me. Yes, it seems to be okay. So I will apply OK here. Now we shall go for selecting directly the element type. Okay, press this button and it asks you to select the regions for the assignment of the elements. So we will select the 2 regions. Okay, done. And we will select standard, family as beam, linear, and the shear flexible as the beam type. Okay for me. So we have assigned the element types also to these meshes. Now next what we can do is that we can proceed for meshing. So okay to mesh the part? Yes. So now you can say that yes, the part is meshed. So it means that the meshing activity is also over in the module. So now we can proceed straight away for the creation of the job. We'll create a job here. So let me see, currently we don't have any job. So we'll create a job. Let me call it as job beam. Okay, job beam. Okay, continue. So keep all the default options also okay. Now proceed for submitting this job for running, submit. Okay, so you can say that yes, the model is submitted. You can monitor the status of the analysis. You can see that it is still running. Okay, and we have some warning messages also that we can check. Okay, and now you can see that the status is completed, which means that we can now straight away proceed to the module visualization. So we can proceed directly to the visualization module. Okay, okay, fine. So let us start reviewing the results. So as you can see that here we have and for CSO 1 to 6 variables which are very important to us, and one obviously is in the axial direction. You can see that there are no forces. Okay, the values are e raised to minus 14, and in the 2 direction also obviously we cannot have any force. So yes, it is e raised to minus 17, Now, if you remember, the loads are applied in the z direction. So obviously, we have the shear forces in the three direction. So go for N4CSO3. Yes. So this is the shear force variation that we are having. So just a minute. Okay, good. So now, if you see the variation, you can say that we have the three critical locations for the shear force. One at the support, at the two supports, okay, and the other at the interior support. We have expected that the same result. So now we would like to know what are these magnitudes. Now, as you can see from this, what we call as this legend box, the maximum shear force that is indicated by the red, it is 29.52. That means at the support we have got 29.52 here, and the deep blue color, that is minus 29.47. So here we can see that approximately a minus 30 and plus 30. Okay, so the shear force at the interior support varies from minus 30 to plus 30, indicating that at the support we have got a reaction of 30 plus 30, that is 60 kilonewton. Okay, and now we would like to know what is the shear force. So from this sketch it is very difficult for us to find out what's the shear force at the support. So what we can do is we can go to tools and query, and in the visualization module queries prof values. Okay, now what you can do is that you can start moving your cursor along the profile of the beam and start seeing how the variation of N4CSO3, that's the shear force, changes. So look into this, okay, dialog box as I move the cursor along the beam profile. Yes, so here we find that the shear force is 16.65. Okay, and here also it is 16.65. Okay, 16.6 kilonewton, and we find that the shear force as expected here, it is around say 29.47, that is around minus 30 to plus 30, and we find that the shear forces are zero at this location, indicating that our moments will be maximum at these two locations. Okay, fine. So that's all about the variation of the shear, and please remember that the applied load here is basically is a linear load. Okay, fine. And the way in which the shear force diagram and the bending moment diagram, the torsional moment diagram, all varies. These are all function of the trigonometric variables, the sin theta, cos theta, etc. So accordingly, you have to review the results very correctly. So this is all regarding the variation of the shear force. Now let me take you to the bending moment. So obviously the bending moment, it will be the, I think it will be the fifth one. Okay, the bending moment will be the fifth one. Yes. So we know that the bending moment. So this is how the bending moment diagram. The bending moment, it changes along the profile of this beam. So as expected, the bending moment should be zero at the pin ends. At these two ends, it should be zero, and at the intermediate support, it should be maximum. That's a negative moment. And in the shear force diagram, we have seen that the crossing of the shear force, that is a affects that is a the shear force V equal to zero. It's somewhere here, and accordingly we find that the shear force zero means corresponding to the maximum bending moment. So this is the location of somewhere the maximum positive bending moment, and in the interior support we have the maximum negative bending moment. And now we can just see the values. We just go for again the prob values. Okay, so let us see how it changes. And please remember that as you move the cursor along the beam profile, you will find that the node ID, the coordinates of this point, and the values of all this output variable, it also changes. Now let us find out what are the values. Obviously at the support you can see that it is 0, so e raised to minus 14 0, and at the interior support we find that the bending moment is a maximum, that is a 35.804. Okay, so this is what is being indicated here, 35.804. Okay, so if you move it a little bit, let me see whether we have some other variables. Yes, it is a 38.6 is the maximum moment. Okay, that matches with this value also. And this is the negative bending moment which happens at the integer support. Now if you are interested in the span moment, you can again move across this. So we find that the maximum positive bending moment is of the order of say 13.6, 13.7. Okay, so it is something like a 13.6, we can say that it's the maximum positive bending moment is 13.6. Okay, fine. And we find that the bending moment is equal to the points of counterfracture are located at this, and you can easily obtain the location from this xy coordinates, and from the xy coordinates you can directly obtain their angular location as well. It's not a big deal. So this is all about how the bending moment varies along the beam profile. Now let us switch over to the torsional moment variation. The torsional moment is indicated by N4CS06. Yes, so this is how the torsional moment varies along the beam profile. As you can see that the torsional moment should be zero, right, at the supports because it's a pinned support basically. And this is a point of symmetry. Okay, this is a point along the axis of symmetry. It means that the torsion will be zero at this point. And so this is how you can say that. This is again, please remember the variation is it follows a trigonometrical function in sin theta and cos theta. So now let us see. So as you can see that the maximum torsion moment is somewhere around the order of 9.375. Okay, 9.373. So what you can do is you can again go for the plow values, and you can directly get what are these maximum values. Okay, you can say that yes, it is a 9.36, 9.37. Yes, 9.37 is the maximum torsion moment that is on the span, and at the support we have zero torsion moment. Okay, so this is how the torsion moment varies along the beam profile. Now I would like to investigate one more variable, that is obviously our deformation u, and you can see that yes, this is how the deformation changes. Okay, so we already have a pinned end. These are the three supports, 1, 2, 3. So obviously we expect that the deformation in so let me go for the u3 in the z direction. Okay, so in the z direction, let me just see it directly here, or u2 minus 2 1. Here magnitude is e2, here it is 0. So you'll find that it is a 0 here, and the maximum bending moment should occur somewhere on the span. So these are the locations, okay, where your bending moment, where your deformation will be maximum. Okay, so this is how the deformation u it varies, okay, along the profile of the beam. So if you want to export the data, as I already explained in the earlier tutorial, you can use the XY data, and you can take all these values. That means the location, coordinates XY, and all the values of the shear force, the bending moment, and the torsion can be extracted. And if you want, you can directly export it to Excel using the tools. Go to the tools, and in the tools you can directly go for, or instead of the tools you have to go for the plugins. In the plugins you have to go for the tools, and you can use the Excel utilities. Okay, so that's all about the tutorial on curved beam. Okay, we will proceed with very interesting tutorials in the coming weeks. So that's all, and have a nice day.